And the weather being what it is, we really needed the last few words that we heard from our chairman. I guess the committee can get ready after these 3 days are over to get into action again. That would be really great. Ladies and gentlemen, at this time it's my pleasure to call upon Mr. Lyle Christiansen, a longtime member of the Kootenay region and the Nelson area, and certainly from what I know of Mr. Christiansen, environment is really something that he is serious about. Mr. Christiansen, our MP in Ottawa.
Thank you very much, Bill and Jan and other guests. Again, it's my pleasure for the second time and to welcome you here to Nelson, this time to Trafalgar instead of LVR. Before continuing, I'd just like to give a special thanks again to the L.V. Rogers Choir and to Bruce Hunter. I didn't know that I'd lucked out so much when I asked them to sing this song and sent them the music for it on September 23rd when we did the candlelight vigil downtown regarding the Global Conference on the Rights of the Child. And not only that, but since then, in fact, just last night while I was down in my office doing some other work, I was taping this music over from a record onto a tape while I was there, and they sing it much better than the professional choir that did it originally. That shouldn't be a surprise. We do a lot of things better in the West Kootenay. The West Kootenay region is not only one of the most beautiful parts of Canada, but apart from that, the people who have lived here and worked here, both for their livelihoods and to create a better environment, a better social, physical, and human environment here, have put a lot of time in over many, many years. Some of that has resulted from some bad things that have happened in this region. One of the reasons why the environmental movement in the West Kootenay has been one of the most hyperactive in Canada was a treaty known as the Columbia River Treaty, and the fight that took place in the early 60s when we alienated forever some of our best bottom valley forest land, whether for recreational purposes or for industrial purposes, but we alienated that land forever, and in so doing also destroyed some of the best farmland and most productive land for human purposes that existed anywhere in this province. The pain that grew out of that and the experiences that people gained during the fight to bring some more rationality and common sense to the management of our resources, with which we had such a close experience during that time, has resulted in a great deal of activism. One of those activists, or two of them, Bob and Linda Harrington, every idea, every event has a genesis, and I don't think I'm mistaken in saying that this series of annual conferences had their genesis in the minds and the actions and the love of Bob and Linda, and I'd like to pay a special tribute to them. I'm very happy that one of my parliamentary colleagues, Jim Fulton, who, as well as having a lot of knowledge to impart, has one of the best senses of humor in the House of Commons, is going to be participating with you this weekend, and he'll have much more of substance to say. But I'm also very sad that another gentleman that I've spent many, many years with, both with him and other members of his family and his father, Stephen Lewis, isn't going to be able to be here because the work environment in which he was involved a couple of weeks ago meant that he was performing an audio-visual presentation. When the lights were turned down, he stepped on the back of a platform, flipped over, and broke his hip. And I know you'll join with me in extending to Stephen wishes for a speedy recovery. Regardless of content, Stephen is an absolute joy to listen to. His command of the language is a work of art. Those of you from this area who were able to listen to him on a very similar subject, actually, in Castlegar just 2 years ago, will understand what I'm saying. Just one or two thoughts. One is that the only people who never fall down are those who never try to stand up. And it's not enough just to know your subject. You also have to begin to know very closely the people, the very, very broad cross-section of people with whom you are going to have to work and be active if you're going to turn the lessons of what you learn into a social and political reality. A gentleman wrote me a letter a little while ago, and in answering him, I responded by saying, I do respect your opinions, though not necessarily your judgment in this instance, and a few thoughts to consider. One, emotion is jolly good petrol, but a shockingly bad driver. You cannot influence people of goodwill by isolating yourself from them, and trust is built by working with people, not lecturing to them. And finally, and this may seem a little obtuse to those of you that haven't been involved in that Machiavellian world that is sometimes called politics, that finally, while it's very emotionally self-satisfying to be absolutely open and direct, the shortest distance between 2 points is often a circle. That's something that we all learn with a great deal of pain, but we do learn it. And if we want to be effective, we have to learn it. Remember, there are a lot of people out there who speak a different language, and I don't mean just French or German, but they come from a different, not only a social culture, but sometimes a very different industrial culture. And if you don't make allies of them at every opportunity, it is going to be much, much more difficult to create the kind of consensus in the society that is going to be required to make the very hard decisions that we do have to make. Just want to conclude with one short comment and the shortest poem I ever wrote, called My Only Demands. It is, give me the right and the opportunity to love, but also give me the right and the opportunity to challenge and to vanquish all that would destroy that which I do love. And I know with you, we love this planet, and that's what I want to defend. Good luck on your road in doing the same thing. Thank you very much.
Thank you, Mr. Christiansen. As a follow-up to the information about Stephen Lewis, who won't be with us Saturday afternoon, I would just like to advise the audience and the group here this evening that Bob Harrington, project coordinator of this conference, and a person who is well-versed in the area of environment, will be taking his place and will be speaking at that particular time. And I'm sure the message that Bob will bring to us will be one that will be very worthwhile for us to hear. As we go along, ladies and gentlemen, over the next day or so, I should say that I'm also a member of the organizing committee. And the reason I'm up here is that I missed a meeting. So you'll have to bear with me for the next few days. What I'd like to do as we go along is, from time to time, recognize certain individuals and thank different groups for the things that they've done and carried out towards this conference. At this particular time, I'd like Val Gibson in particular and the Trafalgar staff to stand, because they are folks that gave up the school for today, and they have been working to set it up for us and so on. So I'd like them to stand and us to give them a hand. I'd also like to deal with one little item that may be a concern. It was brought to my attention that there are some students here that were unable or were not sure about where they're going to be billeted this evening. Is that correct, Mr. Even? Or is that resolved? Right. Yeah. I just wanted to identify for you that we have buses that will be, or a bus that will be leaving this school and heading to L.V. Rogers, where students are billeted at 10:15 after the punch party, which will conclude the evening session. I won't take any more of your time. At this time, I'd like to call upon our Director of Instruction, Pat Dooley, who is also a member of the organizing committee, and Pat will introduce our first presenter for the evening. Pat Dooley, please.
Thanks. I'm really excited to be part of this conference again this year, and really proud of the initiative that this school district has taken. I have the pleasure of introducing one of our speakers for the evening. He's our first feature speaker, Dr. Stephen Schneider. He comes to us, it's his first visit to Nelson, all the way from Boulder, Colorado, where we understand that the mountains are almost as beautiful as the ones we have here. Dr. Schneider is a climatologist with the National Center for Atmospheric Research in Boulder, Colorado. He has a PhD in mechanical engineering and plasma physics from Columbia University, and he tells me that he's interested in climate and how it works, how it affects people, and how people in turn affect the climate. Dr. Schneider has written several books, including Global Warming, Are We Entering the Greenhouse Century?, and several scientific journals. He has appeared on TV shows such as Nova and on a series of radio shows with Dr. David Suzuki. In 1984, Dr. Schneider was selected as one of the 100 outstanding young scientists in America. He will speak to us tonight on global warming. Can we do anything about it locally? Ladies and gentlemen and students, please join me in welcoming Dr. Schneider to Get High on Nature.
distinguished guests. Appreciate your all coming here. When I looked at the weather map, the computer forecast of the weather map before I left, that's the one advantage of working in an atmospheric science laboratory. You get the maps. I said, uh-oh. The only thing I was hoping is that the computer was telling the truth and it would be 5 degrees above freezing, and it did tell the truth. Anyhow, it was especially a pleasure for me driving up from the Spokane airport today, because whenever you look at maps, they often have these little lines along the side saying what the scenic routes were and so forth. And it said that I was taking a scenic route, and I said, okay, well, I've seen these before. You know, you get very blasé. But when I got about halfway up, it really was one of the most beautiful drives that I've seen. It got better as I came in here. The mountains are very different from mine. You have these things out there that are green. Ours tend to be a little grayer and browner. We're drier. Anyhow, that's part of what we want to talk about is, will it stay green? And in order to do that, we need to talk a bit about the global warming issue. Now, I'm sure most of you have heard about it. Anybody here not heard about it? Anybody here going to admit they haven't heard about it? The newspapers carry a great deal about it, and I'm sure you hear talk about how, on the one hand, some people say that the world could be coming to an end from this, and sea levels will rise. Perhaps that's one of the problems. It won't be too serious here, but forests can migrate and other issues. And then somebody else will come along in the next day in some opinion page and say, oh, well, really, there's nothing scientifically solid about this, and we don't know anything. It probably will be good for you, and in any case, it's too expensive to do anything about it. You probably heard that too. And it gets very confusing. So what I want to try to do is put some of that debate in perspective. And since it's a conference on environmental education, the education component is, I'd like to talk about at the end, and I hope somebody will ask me questions about this, if not tonight, tomorrow morning during the panel, which is, how do we approach this as an educational problem? Because what I'll try to convince you is that that argument in the media about end of the world or nothing at all, which in my personal view are the two lowest probability cases, everything else in between is more likely to happen, is a terrible representation of the actual debate going on among the knowledgeable people. And it's hard for a democracy to work, as indeed people who try to make it work know, when a public is confused about an issue because they think that all the experts are confused, and a large fraction of that confusion is because we get communicated a dichotomy of on the one hand and the other, whereas it's really a spectrum of opinion. Well, anyhow, let me show some slides to try to exemplify that. Before I have the first slide on, I read a statistic based on I think it was a Time magazine poll suggesting that in the United States at least, something on the order of 50% of high school graduates couldn't identify on a map all the 50 states. It's a good thing they didn't ask them about the provinces of Canada. They also said that something like 25% couldn't even identify continents. Now, I know that wouldn't be that much of a problem here, right? So we're going to begin, you're not expecting this, with a quiz. Can I have the first slide? Somebody turn on the projector and turn out the lights. There's nobody you see there want to cooperate with this. If you can, eventually it will happen. Yeah, you're fine. You just have to turn around. If you don't mind the stiff neck, you're fine up there. Okay. Now, who can tell me what they're looking at? What is that that's up there? And that was the high school kid who said that, not an adult, right? Lights of what? Europe. Okay, hey, very good. That was, I timed these things. That was 15 seconds. That's the best I've had yet from a public group. And that's from junior high school classes right on down to congressional committees. The fact that at night a satellite can see the dark side of the Earth tells us something. It tells us that our presence on this planet is not just something theoretical, but something tangible. A space traveler coming by would see the outlines of the continents and the cities. Now, let's see how many seconds it takes you to get the next slide. What's that? Not bad, not bad. The synapses fire quickly. I showed this picture in a small town in Vermont, and I was, of course, pointing out all the various cities, and I said, and you're over there. And they said, nope, sorry, you got New Hampshire. It's a good thing I can't reach, because if I try to point out where we are now, I might be in trouble. It's probably one of those up there. Anyhow, the reason for showing this is to remind us again that our footprint on the planet is getting larger, to the point not only that we see it in space, but that we're starting to compete with the natural processes of nature which affect things such as the climate. Now, in those cities, heat is given off. And if we give off enough heat just from heating the houses or air conditioning in cars and in factories and so forth, then we start to compete with the main forces of nature that make the climate, which is, of course, the amount of sunlight that comes in. Now, in a city like New York and Manhattan, the amount of heat that's released there is almost as much as the energy from the sun. And if any of you have ever heard a weather forecast, if you're in New York, it's typical that the forecaster will say, and tonight it's going to be 38 in the city and 26 in the suburbs. And part of the reason for that is that extra heat. It's literally an invisible sun that's on all night. It makes a difference, and we in the meteorological business call it an urban heat island. But from the global point of view, the question is, how much heat do we release relative to the amount of energy from the sun? Anybody have any guesses? Are we 1% as strong as the sun, or a millionth? Courage, come on. Less than one. I've heard less than one. Anybody want to say more than a millionth? Okay, we got more than a millionth. Well, you're right. It's in between those two. The actual number is about 1 part in 10,000. So on a global scale, the amount of heat that we release is not very large. But locally, it's already large enough to make a visible difference. You can hear it in the thermometer readings every night. So we know it's not just a theoretical issue that we're changing the environment. We know for a fact that you can change the climate if you mobilize enough energy relative to the natural flows. Well, the heat released isn't yet at that level where it can do it globally. But it isn't always the things you see. Sometimes it's the things you can't see that affect you. Let's have the next slide, please. Well, before we even go to the things you can't see, let's do one more thing you can. Anybody have any idea what that is? Hint is it's a photograph from space, I'll tell you that much. Yeah, it's a volcano, very good. It's of Mount Egmont, which is in the North Island of New Zealand. And what was so spectacular is to see essentially a circle from space. Now, you see lots of geometric forms in nature, but they're very irregular ones. When you see a circle, you automatically know that nature probably didn't do it. So when I was in New Zealand, I decided to go see exactly what was going on there. Next one, please. Well, there's the volcano, and you can see New Zealand with the meadows and the sheep. It's a beautiful country of about 3 million people and about 60 million sheep. Proceed, please. And we kept getting closer, and then finally, in the next slide, came right up to what was going on. What we're really seeing was the circle is that Mount Egmont is a national park, and that there's a fence, and that up to that fence is the grazing land, and on the other side of the fence is the original forest. So once again, our manifestation on this earth is visible, and if you can see it from space, and it has a different brightness, that means the amount of energy absorbed by the land, the solar energy absorbed by the land, is different. The trees are evaporating water differently, absorbing energy differently. Now, nobody on purpose tried to modify the environment. The reason it's lighter outside in the grazing land is that people in the process of trying to support themselves through increasing their standard of living, through increasing the quality of life, through agriculture or industry or other factors, are inadvertently modifying the system. And the fundamental question that we'll have to get to, which will be a theme of this conference and undoubtedly was one of last time, is at what stage are increasing numbers of people trying to improve their standard of living and using technology and organization, ingenuity to do that, modifying the environment to the point that those modifications start to reduce the very quality of life that we did the modifications for in the first place. And that's what the essence of environmental issues are. And what is different in the issue I'm going to talk about than the traditional one. I mean, this is not new, what I said. This has been known for thousands of years. Chinese emperors learned that when hillsides were deforested so they could see the approach of oncoming armies from neighboring territories, that soil erosion took place. And it was known in London hundreds of years ago that when everybody used coal that you'd have smogs and killer pollution. So that's not new. What's new is not the visible stuff, but the invisible stuff that's starting to grow to a global scale. Ozone is a good example, and the next slide is a scientifically accurate depiction of what's been happening to ozone. Another example of the quality of journalism, at least in the United States. I think this is from the paper with the widest circulation in the nation, the Inquirer. Next, please. Okay. Now, the gas, however, that I want to spend much more time on is relevant to global warming. Ozone is a serious issue, and if anybody wants to know more about it, ask me in the question and answer. But just to get through the part I was assigned, let's take a quick voyage to a very nice place, to Hawaii. And right up there, about 3,000 meters up, something like 10,000 feet, for those of you still in the old units, up on the slopes of that very long mountain, whose name in Hawaii is Mauna Loa, up on the Big Island of Hawaii, an observatory was set up in 1958. And we'll go through some slides. Next one, please. And there it is, up there in that in this very remote area that's supposed to be measuring clean air. Next one, please. In case some of you are wondering what's the black stuff, that's the lava from a volcanic mountain, and the white stuff is what happens when a jerk goes to Hawaii in January and finds the only snow in the islands. The reason they put this there, of course, is because of the fact that Hawaiian Islands are remote. It wouldn't have anything to do with what was happening down lower on the mountain, not with taxpayers' money. Next, please. And there's a little air intake up there, and the next slide shows that inside this little shed is an instrument, and that instrument measures some property of the outside air, and then it measures the property of the standard gas, and for 30 years it's been telling us what's happening to the composition of the atmosphere relative to the standards. And the next one, please. And it was very exciting for me to stand next to that instrument, although it's not exciting for me to see what I looked like 12 years ago relative to now. But the instrument that was so dramatic to me was one that produced a record that literally could change the course of industrial civilization. And that's the next picture, which is, you all knew eventually you'd get a table and a graph, which is the carbon dioxide concentration at Mauna Loa Observatory. And it shows from 1958, and I'll take Stephen Lewis's problem and watch where I'm going. Well, over to 1988, you can see an increase from 315 to 352. That's 315 parts per million. That's not a lot. That's about 0.03%. So this gas is only a trace gas in the atmosphere. It's increased about 10% over that period of time. It also has a cycle on it. That cycle is interesting in itself, because if you look and see when it's lowest around September. Now, what happens between September and March that would make carbon dioxide in the air go up? You've all had biology, right? What happens is the sun goes to the other hemisphere, and instead of having photosynthesis winning the race between taking CO2 in and out and making oxygen, respiration and decay win the race. So all the leaves that grew the previous season decay, and they give back the CO2. Then in the spring, the sun gets high in the sky, the grass gets green, the leaves grow. Where did the mass for those leaves and grass come from? From the air, from the CO2. It's part of nature's breathing. What's different is the growth. Now, we know, despite all the controversy you hear about the issues of global warming and so forth, we know for certain, well, let me revise that. Nothing in science is ever for certain. Everything is always forever tentative. It's just that some things you believe more than others. But we're very, very sure that that's due to us. The burning of fossil fuels, coal, oil, and gas, deforestation, are the principal activities that put CO2 in the air. We also know by looking in the ice cores, by ice caps rather, where snow falls and is preserved for literally 200,000 years, if you drill a hole in the ice and you take a chunk of ice back, you can take it from 1,000 meters down or 2,000 meters down in Antarctica, you have air bubbles that are trapped in the ice that were put there at the time that ice was originally snow. So what you're actually looking at when you take this 2-kilometer core is you have a library of the history of the Earth's atmosphere. You can analyze the gases that our Neanderthal ancestors were breathing. You can find out what the air was like. And as a result of that, we found out that it has never had carbon dioxide in the atmosphere much above 300 parts per million until the Industrial Revolution. It's virtually certain that we're the culprits on this one. And the question is, so what? Is it important? Well, the reason that carbon dioxide is important is, A, it's involved in all ecological processes that involve photosynthesis, and the second reason is it's a so-called greenhouse gas. It's part of the greenhouse effect. That's a complicated thing to explain, so I apologize that the next slide is so technical, but it explains very clearly how the greenhouse effect works. At least that's an effective way to sell magazines. The next one, unfortunately tells you how it really works. And let me spend just a second on it. If you take the yellow, which is the amount of incoming sunlight, the prime mover behind our climate, and you say, what happens to the sun when it comes in? You break it into numbers. A number 100 means 100% of the sunlight. It's really about 340 watts of energy averaged over every square meter of Earth is how much sunlight we get over a year. And if you take that, call it 100 units, about 25% is reflected from clouds, about 5% from the surface, 45% or so is absorbed, about 29. Really, these numbers should be plus or minus 5, but we know it pretty well. We just don't know every detail. Most of that's evaporated water, which makes clouds again. All that seems pretty straightforward. You know, if you heat the surface, you get evaporation, you get heat that rises. But the Earth's surface would continue to heat up if those were the only processes involved. It would be much different than it is. So what happens is the Earth cools by giving off another kind of radiation, so-called infrared radiation. And you've all experienced that if you've ever been by a fireplace or a fire. Obviously, if you put your hand on top of it, you get burned. But that's not due to radiation, that's due to the convection, the rising air. But if the fire's over here and then you step aside, you can feel it on your face. Or if you go by a cold window, you can feel the cold on your face. That's this infrared radiation that you can't see, and it's there all the time, and it's just as important as the sunlight in controlling the Earth's climate. Well, the gases in the atmosphere, water vapor, the clouds, carbon dioxide, methane, those are natural gases, as well as man-made ones like chlorofluorocarbons, the ones that are depleting ozone, all have a property that they let sunlight through more easily than they let infrared back out. So they block, trap, and re-radiate down to the surface something like 88 units of heat due to the natural greenhouse effect. Now, a lot of you said, oh, the greenhouse effect's a terrible thing. Well, I have to change your mind. The greenhouse effect, the natural greenhouse effect, is a wonderful thing. If it weren't for the natural amount of water vapor and carbon dioxide and methane in the atmosphere, the Earth would be about 33 degrees or so colder than it is now. And it would not be a very pleasant place for growing orchids. Quite simply, our evolution depends upon the natural greenhouse effect. And in fact, the greenhouse effect is not a controversy at all. And it may fool some of you because you say, but the newspapers said it was. What they really mean when they say the greenhouse effect is a controversy is the addition of man-made chemicals, man-made chemicals like carbon dioxide, chlorofluorocarbons, methane, and so forth, some of which exist naturally. It's our addition of these things as pollutants competing with and adding to nature. That's the controversy. And the issue is the 33 degrees warmer that nature has made us, is that going to be 32, 35, or 37, or 40? Is that going to happen in 50 years or in 100 years? That's where the controversy is, not about the greenhouse effect itself. In fact, I remember once after a press conference talking with, fairly certain terms about the seriousness of the greenhouse effect, and one of the reporters, I think he was from the Wall Street Journal, said, oh, wait a minute, he said, you can't tell me that the greenhouse effect is that certain, it's just a theory. And I said, well, you're right, it is just a theory, but then again, so is gravity. So if you'd come up here on the stage, stick your head in my guillotine, we'll perform the billionth experiment to see if gravity still works. He didn't come up. The issue is not whether something is or isn't a theory, that's just a polemic. The issue is how well validated is the theory? How much information have you got to find out how good it is? In the case of the natural greenhouse effect, it's validated beyond doubt. Where the debate comes along is if you add the 25% more carbon dioxide in the atmosphere since the Industrial Revolution, the doubling of methane, the addition of chlorofluorocarbons, we know that that's trapped about 2 watts of energy, extra energy, over every square meter of the Earth since we've had an industrial presence. How much is that? That's like one of these little Christmas tree bulbs every meter, except you can't see it because it's in the infrared. That part's not controversial. Controversy is translating that 2 watts of extra heating into degrees of temperature. Should it be 2/10? Should it be a half? Or should it be 1 or 2? In order to do that, you've got to build some model or theory of how the system works and then quantitatively try to evaluate it. And there's legitimate controversy and plenty more to do. The problem is this isn't an experiment that is an academic one only. This isn't just simply fun and games for those of us who build computer models, and try to talk our governments into giving us bigger computers and more programmers. This is a game that's being played on this planet. So the experiment isn't just simply one in the microchips of a Cray, that's a fast computer. It's one that's going on at the same time on laboratory Earth, except this time the mice in the cage are us and other living things, and that's why it's a politically important issue as well. Now, I'm going to come later to how we do these models, whether we can answer the questions in time, and the nature of those various debates. Okay, let's proceed. Oh, I had to be fair to the competition. This was Newsweek's discussion of it. My friend, the population biologist Paul Ehrlich, saw me show this picture once, and he said, Schneider, that has nothing to do with the greenhouse effect. That's the solution to overpopulation on the Earth. Next. Oh yes, let me. This is the last slide in the new science of coverology. This is a scientific magazine, Discover, and I was amused that they started melting the Earth from the South Pole, the one place that we probably wouldn't melt even if we heated up 10 degrees. In fact, when I showed this picture in Australia, they were not very amused. But the article was very good, though. You got to get people's attention, right? Okay, next. So far, I've been talking about the uncertainties having to do with chemistry and physics and biology. But actually, the biggest uncertainty in the whole problem of global warming turns out not to be natural science. It's really social science. It's human behavior. It's what are people going to do? This set of curves shows projections of carbon dioxide from 1980 to 2220, way out into the future. And it's all over the place. Here's the value in the Victorian times. 600 is a doubling. So if you jump from here to there, you've doubled the amount of stuff in the air. That's an unprecedented thing in our geological epoch. You have to go back near the age of the dinosaurs before you start getting large increases in CO2 naturally. Well, if energy grows at 4% per year, and you use a standard mix of fossil fuels, then you double CO2 sometime early in the next century. But if it grows at 2% per year, then it's the middle of the next century. Or if you take Amory Lovin's advice and you have a very strong energy efficiency program coupled with renewables, you can actually hold the amount stable. So there's a whole range of possibilities. Now, how do we evaluate this? Let's look at this. I went back to Ehrlich again. He and John Holdren years ago were in a debate with Barry Commoner. Any of you know who Barry Commoner is? He's an ecologist who was arguing that environmental problems were largely structural. They were social problems, they were problems with our values and our technologies. And Paul was arguing that population was a large component. And they were having some nasty fights about this. And John Holdren, who's a physicist, got in the middle and said, would you guys stop fighting because you're both right? And helped come up with this equation. And I think it's the only one I'll show you. And it's what they call the population multiplier. And it says, what's the total emission of something important? Well, in this case, we're talking about carbon dioxide, so I'll use that. The total emission is the product of three terms. The first one is CO2 per technology. What does that mean? Well, that means what is the engineering system you're using? If you're using coal, you put out twice as much CO2 for each unit of electricity you generate than if you're using methane, natural gas. If you're using solar, then you don't get any, or nuclear, except that which it takes to build and decommission the power plant. Now, I'm not arguing for or against anything yet, just saying this is how you do the analysis. The second term, so you have to project that in the future. The second term is technology per capita, which is a fancy way of saying standard of living, something that's fairly high, or very high in the case of I almost slipped and said North American countries, but Mexico's in North America, and it's not high in Mexico. It's certainly high in the US and Canada. In fact, it's as high as it is anywhere in the world in terms of energy. It's not high in developing countries, and indeed, they want it to be higher. And if you ever go to international meetings, you'll find without exception that to be the arguments you hear from their diplomats. And the third term is population. Now, it's the product of all three. Now, in the US, I've given talks where I've shown slides like this, and somebody once got up and accused me of ideology because I brought in the P word. That's a problem we've had in the US lately. You can't even talk about population control as if somehow this is immoral. I mean, to me it's immoral not to talk about it. But the problem is there's no ideology up there. That's a statement of the conservation of mass. I mean, the amount of stuff you give out is equal to how much comes out from the technology used times how much technology each person uses times the total number of people. It's straightforward. Now, that puts an analyst in trouble. How do you project the future when these are essentially unforecastable reliably? Well, you do what any analyst does. You invent a way out of it. You make scenarios. You say, what if? And that's what this chart shows. What if we grow at 4% or 2%? And then you say, what happens to the climate? Does it warm up 2 degrees or 4 or 6? What happens to the forests of North America? What happens to sea levels and coastal areas, how the ticks move and diseases. And if you don't like some of those scenarios, then you say, well, wait a minute, maybe we better change our habits and get on to one of those other curves. So it's not that we're making a forecast of what will happen. We're showing what the consequences are if things continue as present or if they increase. The present is somewhere in this range in here, and if you talk to a number of economists, they wish they were on the faster growth curve. When you talk to environmentalists, they want to be on the lower one. Now, those differences are values, not science. Okay, what we do then is we'll look at fast and medium and slow growth curves and say, so what? Okay, let's proceed, please. That was just fossil fuels. What about deforestation? The CO2 has increased about 10% in the last 30 years in the air, and probably about 25% of that is due to deforestation, because a tree is a big chunk of carbon that was taken out of the air. Well, it was taken out of the air, so why is burning it not just giving it back? Well, it is giving it back, but we're burning it in 20 minutes, and normally it decomposes in 20 years or more, so we have a rate buildup. Plus, you replace big mature trees with an impoverished environment, particularly in the tropics, and you have less total carbon, so there's a net release to the atmosphere. So this isn't just a problem of the rich having profligate standards of living. It certainly is that to a considerable degree, but it's also a problem of people using deforestation, and the deforestation is not driven out of stupidity, it's driven out of desperation, again, from heavily populated cities. People get pressed out into the country, literally mining their forest regions because they don't have any other, in their opinion yet, clear alternatives. So all countries in the world contribute. The next slide shows that one of the principal greenhouse gases, methane, is produced in animals and in rice paddies, and again, that's true in developing countries just as here. The methane is produced where there's not a lot of oxygen, and a rice paddy is a perfect place because you flood it, you have a lot of organic matter, and since you don't have air, the next slide shows what you do get is a rice plant is a little straw, and it just sucks the methane right up and into the air. Methane's doubled since the Industrial Revolution. It's probably about 20% of the heat trapping that's gone on. Animals, which many people consider an important part of dietary standards of living, particularly in developing countries now that want to increase their dietary intake of animals. Animals are a major producer of methane. In fact, this is a terrible after-dinner topic, but I have to tell you. I once was having dinner with a biologist and one of his students, and I said, okay, I have to get graphic. How do you know how much methane a cow puts out? What do you put, a bag in the front and the back? I mean, how do you do it? And he said, no, we're much more sophisticated than that. We get a few animals in a shed, and we make the shed airtight, and then we give them special diets, and we monitor, we go inside and we monitor the air that flows through, and the student is laughing. I said, what's so funny? He says, well, everything he said is true except when he said we go in. I'm the one who goes in. Nonetheless, animals, again, are part of the problem. It's back to what I said in the beginning. People who developed agriculture, developed animal husbandry, this was not a deliberate plot on the part of people to disrupt the environment. It was simply pursuing increased standards of living without thinking about what the consequences were. And what we have to come back again and ask is, when do those consequences get severe enough? When is our footprint on the face of the earth large enough that we have to start changing the ways? And you're not going to find a single answer to that. I'm not going to pretend that there is one, because how far to go and how much risk to take is all a question of values, not a question of science. But if you don't understand the terms of the debate, it's very difficult to participate meaningfully in the debate and get your values expressed to your official representatives. Okay, the next one, please. All right, now, let's say that we make some scenario. We're going to have CO2 doubling in the early part of the next century or late. How do we translate that into climate change? Well, you can't go back into nature and say, what happened the last time CO2 doubled in 50 to 100 years? Because it never happened, as far as we know. If it did, nobody was measuring it. So we can't use natural metaphors to give us exact answers. Well, we can build a laboratory model, pollute it, see what happens. Well, you can't do that either, because nobody's been able to conceive of any lab model remotely complicated enough to describe the earth, the oceans, the clouds, the biota, and all the interacting elements. So we do the best we can by simulating it mathematically inside the microchips of, in this case, a Cray computer. Okay, we use models. Now, you'll hear about them. They're controversial, so let me spend a few minutes on the next one, please. What is a model? Well, it's equations. It's equations of the conservation of mass and energy and Newton's laws of motion and ideal gas law. It sounds very fancy. Any of you had physics, you say, hey, that sounds like, laws that are pretty well known. So why aren't these models good? Because they're based upon proved, remember, you can never prove anything but essentially proved laws. Well, the reason is that nobody can solve the equations. They're too complicated. So you can't solve them exactly, you have to approximate them. What you do is you take all that fancy calculus and you reduce it back to arithmetic by taking the continuous atmosphere, dividing into chunks or discrete blobs or grids. And the next picture, I think, shows you an example. So you cover the Earth with a mesh, and instead of solving for every gust of wind, you have little chunks that are about 4.5 degrees latitude by 7 degrees longitude typically, and then you have, say, 10 layers of them, about 20,000 of these grid boxes around the world. Okay? This is what a grid looks like at that resolution I just told you. This isn't the real geography of the world, that's the geography of the computer world. In fact, recently, Prime Minister Thatcher was visiting Colorado and came out to one of the 2 places she visited was my lab, the National Center for Atmospheric Research, and I was one of the 6 people that had got the chance to make a presentation. And when I showed this slide, she was none too pleased. I think I made some joke about it, and the empire doesn't count climatically anymore either. In fact, one of her own scientists had showed her one that didn't have Britain in it, and when she said, can't you do better? He said, well, if you give us twice the computer budget, we can. And they got it. Unfortunately, the U.S. is too big. Actually, she was not nearly as upset as was the Japanese ambassador when he saw this. What we generate, in the next slide shows, is we generate weather maps. Every 30 minutes we get a weather map around the world, and we run it for a year, say. Now, a year of simulated weather is 10 hours on one of those crays. So if we're going to run a scenario, we have to run 100 years in the future. Well, that's 1,000 hours of computer time on one of those crays, and 1,000 hours at $1,000 an hour, which is what they cost, is $1 million. That's not how much time I get in a year. That's what my whole group gets in a year. So there are very few such runs made, 3 or 4 in the whole world. There's a good group in Atmosphere Canada, the Canadian Climate Center, that does the same thing, and they have the same problems that we do. We're very limited by computing resources. Now, it's not, I have to be blunt, this may sound like a sales pitch from somebody who's a special interest, and it is, but the computing power exists on this continent to be able to make 10 times more runs than we make, but currently it's dedicated to a different issue, and you can guess which department has the computers, and it's not the ones in the environment. Okay, let's go on. So this is typical of what the models do. They give weather maps. This is hot weather, cold weather. This is present climate. Sometimes I have a nice video of this, but not tonight. And then we double the carbon dioxide, and you can see that you still get cold weather. You still get a blue, but the probability is much less. So you have a lot more red, meaning it's more likely to have heat waves. Now, you had a pretty good one around here, didn't you, this summer? Now, I'm not going to argue that that's because the world's a ½ degree warmer and that was due to greenhouse gases, although I consider both of those quite reasonable prospects. But nature is very variable. The way to think of it, that's what I like in that picture, is it's like a big pair of dice, except not with 12 faces, with maybe 1,200. Here in the present world, you see roughly an equal number of warm and cool extremes. And in the disturbed world of the computer, you've loaded the dice. You've erased some of the cool faces or erased some of the wet faces and replaced them with hot and dry. Now, nature will continue to fluctuate, and the question is, at what stage will we be sure that the dice are loaded? That is, that we've really changed the system, and now year 1990 wasn't just a fluke, just like 1988 in the United States with a heat wave. Well, the answer is it's going to take us 10 or 20 more years to establish that to a statistical certainty of 99% that we scientists like. In fact, many of my colleagues say, well, it's irresponsible for you, Schneider, to go out there and advise people to change the building codes to make energy efficiency better until we're 99% sure. I mean, you could be wrong. They're right, it could be wrong. And then I generally ask such people, do you have insurance? Are you 99% sure that you, rather than the insurance company, is going to win over the course of your lifetime for buying insurance? In fact, if that were the case, the rock of Prudential would have crumbled a long time ago. Why is it that people buy insurance? It's not because of 99% certainty. It's because you can't afford to take catastrophic risks, even when the odds are against you. And this is not an issue that's going to have 99% certainty before 10 to 20 more years. The problem, again, is it's not an academic experiment being performed by some of us for fun in computers. It's a real one. And we're in a race, which is to try to see if we can figure out what's going on at a faster rate than we're insulting the environment. And right now, I think we're losing the race. And I honestly think that my profession will not give you definitive answers before the thermometers of the world will tell us what's happening, at least at the current rates of study. Now, this is typical of what the models project. It shows, the red shows summer soil moisture being dried in a doubled CO2 world, and it suggests dry throughout, sort of like the 88 or 90 scenario, dry throughout mid-continents and mid-latitudes, and wet in India and so forth. The problem is, these are big changes, 30 to 60% drier, 20 to 100% wetter. And I would ask you all to please take this very seriously. Those are not trivial numbers. However, do not take it literally, because the details that this model projects, I could show you another model that would look different, and another one that would look different. What would be common to all of them, and what I believe will happen, is that numbers like 20 to 60% differences in soil moisture will be real, but we don't have the capacity to reliably forecast the distribution of exactly where and when it's wetter and drier, only that the statistics of the past are no longer a very good guide to the future. That should make anyone in the water supply business, forestry, agriculture, or just plain interested in ecosystems nervous, because these are not trivial changes. Next, please. Well, this summarizes all the uncertainties that you can get. This is from an international assessment body called ICSU, the International Council of Scientific Unions, is incredible alphabet soup in all the bureaucracies. This one's an international one. What it shows is the temperature of the world for the last 150 years, and that's a little bit more than ½ degree Celsius warming. Not continuously, it goes up, it goes down, and back up. The 80s, this was up to about 83. The warmest year was 88. In fact, 90 is the new record so far, but it's too soon to know. The 80s were the warmest decade in the record. Is that because there's 25% more CO2 and 100% more methane? Could pretty well be. In fact, I think it's likely to be true, but that's not a 99% sure statement. So you will hear scientists fighting and screaming that, no, there's no evidence, says one statistician friend of mine, that that isn't a natural trend. Nature could have done that. It's not unprecedented. It's happened twice in the last 3,000 years. You know, 1 century warmed up ½ degree. The problem is, all right, you're right, it's not 99% sure, but that's not the same thing as no evidence. I mean, the evidence is at the 80, 90% level. Could be chance. It's, again, back to planetary gambling. But this is the most important point. Supposing we're lucky, supposing we have a breakthrough in solar power, it gets cheaper, people get smart, and we stop polluting, and we have a big crash program for population control, and the Chinese don't use coal, and instead they use biogas, and the Japanese and we and others help them with the most efficient technologies, every good thing you could name from the environmental point of view, and then all the feedback mechanisms in nature that I haven't talked much about, because our computer models try to account quantitatively for whether clouds get bigger or taller, which can either make the warming more or less. They try to account for how ice comes and goes. And all of those accountings are not very accurate, maybe a factor of 2 or 3 uncertainty. So let's assume that we're very lucky that the feedback processes are negative or stabilizing, that the population's not going to go up much. The lowest projection that you typically see is around a ½ degree warming, okay, by the end of the next century. What happens if the opposite takes place? Nobody listens. We have 15 billion people. All the coal is used. Nobody controls anything. And the feedbacks in the system are positive, and it turns out that our uncertainties come out so that we've underestimated the impact rather than overestimated. And then the upper level shows about 5 degrees warming before the end of the next century. You know, 1 degree, 5 degrees, doesn't sound very serious. Well, 1 degree, what's that? It's not too much, I've heard many people say. And at first it might not sound like much, but let me just give you some background. 15,000 years ago, the great ice sheets that stretched from Long Island across to Wisconsin, and then the expansion, I guess the one here had pretty much started to go by then, geologists here can tell you, better than I remember the exact map, but the world was still coming out of its ice age about 15,000 years ago. It took 10,000 more years to get rid of that ice. What happened was the sea levels rose 100 meters. The forests of North America moved thousands of kilometers. That nice maple leaf that you see up there did not exist in Canada. Those trees were buried in Georgia and North Carolina in minor amounts then, and what's now the main forests of the Middle Atlantic states and the Atlantic provinces were boreal forests at the time. It's now up in central Canada. And those forests moved over the 10,000 year period, a couple of thousand kilometers, in some cases, less than others. Species went extinct, others evolved. Quite literally, the ecological face of this earth was revamped by that ice age's elimination of 10,000 years. Now, we didn't do it, that was nature. But the key is, anybody want to guess how many degrees global average temperature change that represented? 5. So 5 degrees is a very big number in planetary terms. The scary thing about this chart is not just the 5 degrees, but the fact that that curve, if it were true, takes place in about a century. So we're talking about a rate of change 100 times faster than natural rates. Now, it would be arrogant nonsense for me to get up here and tell you that we scientific professionals, as ill-equipped as we are to understand the present distribution of species on Earth, the present climate, are going to be able to tell you the exact consequences for forests, for water supplies, for human health, for sea levels, for severe storms, of a system out of balance at 100 times faster rates than nature has done in a long term. We simply aren't that good, and I doubt we will be for the time frame of 10 or 20 years. Now, what's the policy question of relevance? Obviously, what's the probability of this, and what's the probability of that? I mean, if this is 1 chance in a million, we're getting around the same odds of the Earth being hit by a big asteroid, which would be even worse than any of this. That would be worse than a nuclear war, and there's nothing you can do about it. So 1 in a million is not the kind of thing that people routinely spend very much trying to do about. I would argue that it's about 1 in 10, that upper one, and I'd also argue the lower one is probably 1 in 10, and everything else in between is coin flip. Had an argument with a U.S. State Department official 2 years ago before an international committee meeting about this, and he was saying, why are you advocating that we should do something about this? And I'm going to get to that in the remaining 10 minutes I have. Why are you advocating we do something about this issue if the uncertainties are such that we could end up with a negligible effect? Well, first I said, well, wait a minute, a half degree in a century, that's still faster than normal, but I had to admit that a half degree change in a century is not so terrible. Not at all. And then he said, well, then you're advocating, you want us to spend billions of dollars and alter plans, and you could be wrong. I said, you're right, you could be wrong. But then I asked him, I said, so what do you think the odds are that that'll happen? And he thought, and he said, I don't know. I said, let me help you. I said, how about 1 in 3? He said, all right, maybe a little higher. I said, yeah, I'll tell you what, I'll give you 1 in 2. I'll give you a 50% chance that all the uncertainties involved with the human behavioral assumptions, biological sciences, physical sciences, are such that the answer is going to be in the lower half of the projection currently made by most world scientists. You know, we're down here in this category. He said, okay. He said, I buy that. Then what do you want to spend all that money for? I said, because it's obvious, because the sword of uncertainty has 2 blades. You know, what we don't know is as likely to make the problem worse up here as it is to make it better down here. So what we're really looking at is a planetary gamble. You know, we got this coin. We flip this up in the air, and one side says, well, lucky, moderate to light change, and the other side says, oops, unprecedented to catastrophic change. When you have a coin like that, in my value system, I don't want to sit and wait for it to fall on the ground. I'd rather do something to slow it down. Now, even if that means spending present resources as a hedge against a future change whose details I can't guarantee, the same reason that we buy insurance. In fact, I asked him, do you have insurance? He said, yeah. And he, of course, knew what I was getting to. I said, well, why don't you just wait? Oh, I forgot. He told me, he said, well, why don't we study this for 5 or 10 more years? And that way we'd know better. I don't think in 5 or 10 more years we're going to have the capacity to answer these questions any better than we can now. A little better, I think. We might have, but that's a gamble. And I said, why do you buy insurance? Why don't you wait until you break your leg or get an appendicitis or have nothing? And he sort of smiles at, because you know they won't sell it to you after that happens. You have to buy insurance in advance. And the question again here is not one of scientists giving you truth. It's one of scientists giving you possibilities, scientists giving probabilities, and then you have to ask a third question, which is how do you know? And the probabilities that I've been giving you, there's no way to calculate those. Those are intuitive. They're the best judgment of knowledgeable people. Don't just ask me, ask a lot of people. And that's why I was getting angry before at the kind of press wars where the opinion pages put these extreme views in, because what they don't represent is the vast majority of knowledgeable opinion that falls in between. And if the public hears that the scientists don't know, they say, well, what the scientists don't know, how can I know? Let's just wait and see. Whereas the reality is the vast bulk of scientists would say we don't know the details, but say we know something about the magnitude, and would give very high odds that the truth falls out in that range, and it could be up there. Now, that's a tough message to get across on the evening news. And any of you ever try to get on an evening news program, at least in the United States, there's sort of two ways I could describe this problem. I could say, well, you know, there's a median probability that we'd have 2-degree Kelvin temperature rise, which is large compared to any in the Holocene. That will not get you on the evening news. The alternative is I can say there's coin-flipping odds of unprecedented climate change over the era of human civilization. That will. That'll also get your colleagues to call you irresponsible. But in fact, those two are absolutely equivalent statements. And then they get somebody else on who will say something else, and it's up to you, the public, that's getting exposed to a variety of things, to go beyond the bumper stickers, the headlines in the news, and find out what really is going on, so you can learn how to apply your values about how to take planetary gambles. Because the real issue at stake about what to do either locally or globally has to do with whether you fear more investing present resources as a hedge against future change, or whether you fear having that change come on without trying to slow it down given the range of possible outcomes. Now, I promised I'd talk a little bit about what to do. What are the kinds of things that we can do? Well, first you can do something at home. You can have a light that you don't need when you walk out of the room on, like now I have a slide projector that I don't need, so I could ask to have him turn it off. And if you walk out, thank you, turning it off. If you, leave the fan on so I don't burn my slides. If you, for only a minute though. If you walk out of the room, how many of you, I want the truth, forget to turn the light out? Come on, I do it too. Now my kids are reminding me, because I've been beating on them, and now they're reminding me because they have a better memory than I do. What is the purpose of doing that? Well, one person turning the light out when you walk out of the room isn't going to make a lot of difference. But 1 billion people doing that 1,000 times a year is. The second thing is it gives you the right mentality. It says, I don't want to waste. Now, you haven't done any degradation in your lifestyle. It doesn't hurt your lifestyle to have the light off when you walk out of the room. Now, it would hurt your lifestyle if you took one bulb out. You might, not be able to see as well, and that's the difference between conservation and efficiency. Efficiency says you want to get a brighter, you want to get a bulb that's more efficient, that gives twice as much light for the same heating. That's the second thing you ought to do. You ought to be efficient. First thing is don't waste, and the second thing is conserve when you can. For example, you have an errand to run. You have 3 errands to run. You have to pick up the kids, you've got to go to the store, you've got to go over to the library. You could make 3 trips. Or you could think for about 30 seconds and figure out a way that you could make 2 or maybe even 1 trip to combine the errands. Not only will you be helping the environment by putting out less pollution, you'll be lowering balance of payments deficits, lowering the military expenditures to defend the Persian Gulf, lowering acid rain. In fact, somebody calculated it was $94 a barrel to defend the Persian Gulf, and that's not part of the price of energy yet. In any case, the key is, and you're going to lower your bill. So you're going to win by doing that. These are the sorts of things, they will not entirely eliminate the problem. That will require more draconian measures, as we'll hear later on, Bob. There are fundamental lifestyle issues associated with completely eliminating the growth of these gases. But you can make a 10% difference with these kinds of habits. And nobody should ever put down a 10% difference, because 10% here and 5% there, you nickel and dime long enough, you get half of it. And the first things that we're going to do that are politically acceptable is let's do the nickels and dimes first. At least we're taking the steps in the right direction. So then you want to plan the trips. Then the next thing you want to do is you have to buy a car. Well, do you really need a pickup truck that gets 12 miles a gallon when the only thing you put in the back of it is groceries? You know, the urban cowboys of many cities do that. It's an indulgence which I think is no longer responsible. If you need a pickup truck for your business, that's fine. But if you're playing, that's where we need some lifestyle change, is you don't need to have something larger than the service it provides, because you're just simply putting more stuff out than you need. By the way, when you get the more efficient one, it's going to save you a lot of money and probably give you more disposable income. You'll have more fun with it. But again, that's a value issue that we have to confront. Most people aren't buying the pickup truck when they don't need it because they want to hurt the environment. It's because they don't think about it. That's where education comes in. We need to find what the connections are of our activities. Then, when you go out to buy a refrigerator, do you read, at least in the U.S., the yellow labels, which tell you how much energy it uses? You have one for $500 and one for $550. Now, most people, they look the same. They buy the $500 one. Of course, if they read the label, they'd find out the $550 one has better insulation and it uses $10 a year less electricity. That means in 5 years, it's paid you back. In 10 years, it's doubled your return. That's a pretty good investment. It's not bad. But you have to be trained to think that way. What do you do in your house? Our building codes, how tight do they require us to insulate? Do they require that our windows have what we call heat mirror, which is now, it's a space age product, but it's now relatively cheap. Do our light bulbs that we use, are they the standard incandescents, or are they tungsten halogens, which are twice as efficient? Or are they compact fluorescents, which are 4 times as efficient? These lighting fixtures already exist. I've spent a lot of money learning about them, putting them in my house. I'll give you an example. A compact fluorescent costs about $10. It's about 18 watts, let's say, and it puts out as much energy as about a 60-watt bulb. So it lasts 10,000 hours. A standard bulb lasts 1,000 hours and costs 50 cents. So how many people, admit it, how many of you are going to buy a funny-looking bulb that costs $10 when the one next to it costs 50 cents? You fools. You're a bad bargain. And I'll explain why. Most of you wouldn't. I appreciate your honesty. I didn't at first either. I had to be convinced, and when I was convinced, I felt like a fool. Here's the story. One lasts 10,000 hours, the other 1,000 hours. Okay, that means you have to buy 10 of the 50-cent bulbs for one of the $10 bulbs, all right? Still sounds like you're a loser, right? After you buy 10 of the 50-cent bulbs, you spent $5. So you're still out 5 because you had to spend 10 for the big one, for the other one. Of course, if you're a business and you're paying somebody $10 an hour to change those bulbs, you're not a loser. But let's just think about doing it at home now. How much energy do you save? Well, at 10 cents a kilowatt hour, or 6 cents, pretty standard number. Maybe it's lower where you have hydropower, but even at 6 cents a kilowatt hour, what you're saving is about $40 over the lifetime of the bulb. $40 in electrical cost. And if you're in a hydropower place at 2 cents a kilowatt hour, so you're only saving 20. You're still a winner over the 10,000 hours. And most people just don't think that way. And as a result, the stores aren't stocking these bulbs. And if they were stocking them in mass, then the price wouldn't be $10 anymore. It would start coming down. Economists have a way of describing this. What they say is there's a gap between current practice and best practice. And in other words, how do we get into the marketplace things that save us money that really work? And this is, again, partly an educational question, partly an information question. And part of it is also human nature. When I first asked my electrician to get me fixtures that would take the compact fluorescents, he tried to tell me they were freaky and nobody wants them, they don't look good, he gave all these reasons. And I said, and you probably don't have them in stock. And he sort of said, well, I said, well, order them, this is what I want, and if you don't put it in, I'll hire somebody else who will. Now, most people won't do that, but he did. And he was at first frightened by this and put off. But after he put them in and after we're there, he now sends people to my house to look at them so that they will, now that they have a demonstration, they'll buy them. The key is getting people past fears, past habits, past traditions. That's how you accelerate current practice toward best practice. It won't happen by accident. It will require positive action, both from you as individuals and from governments. For example, local governments, state governments, national governments, they all have building projects. Why can't they make demonstration projects using the best energy efficient technologies, the best lighting, and then invite the tradespeople in to be part of the process of doing it, to be proud of it, to own it, in other words, And instead of opposing it because it's different than what they've always done, they wouldn't be scared. These are the kind of things where some judicious initial investments made at local, state, provincial, and federal levels really can make a difference. Ultimately, however, and this is the toughest part, most of us, I mean, in this talk I said we talk about what to do locally, but if we all did it alone in our own one town, our own one state, or even country, we only make a few percent difference in the world. Now, I gave you the speech about how don't ever put down a few percent, but I've heard this kind of argument from a coal company executive who said, wait a minute, he said, the United States is only 25% of the world's CO2, electricity is only a third of that, and coal is only a third of that, so why do you want to kill our industry for only a 3% difference in the world? My gosh, if the Chinese made even a third of the promise they make to use coal with their population for their growth plans, they'd swamp us and we'd be out of business. And then I heard from a General Motors executive, he said, well, the U.S. is only 25% of the world's CO2, and the transportation sector is only 25% of that, and we're only 25% of the transportation sector, so why do you want to bankrupt us when we're only 2% of the problem? I've heard from 50 different people that they're only 2% of the problem. And they're all right. But what's the issue then? Everybody has to do a little. And the question is, how do you get started? One country does it as a unilateral action. Oh, we're a fool because then our prices go up, nobody else's do. On the other hand, if nobody takes the first step, nothing happens. So what do? You take a first step, and then you invite others to do it, or if they don't, you get tougher by putting tariffs on their products that don't to reflect the energy increase that you put on your energy tax. I mean, there are a variety of things you can do. You and I can't negotiate with the Chinese, but what we can do is we can send messages to our legislators, to members of parliament, to other officials, local and state, saying, when you come and tell us that you're going to help improve the economy, help provide jobs, we accept that, but we also want you to do it in an environmentally sustainable way. And when they tell you, not all will, some will, tell you that that can't be done without bankrupting the country or without disastrous economic consequences, you tell them that is just simply not the facts and that you'll vote for somebody else, thank you. And that's the spectrum of things we need to do, from literally turning the light off to changing the public philosophy that has legislators worrying more about immediate jobs than long-term jobs. For example, in the U.S., if we had a tax on carbon in proportion to the amount of pollution, it would be very detrimental to the coal industry. It would substantially reduce the acid rain problem that's been a friction between our countries. It would also reduce global warming and so forth. Well, why hasn't it happened? Because there are organized groups that say, we will be the victims. There's poor people in cities say, we will be the victims if you increase the price of energy. And they're right. So part of the issue is not just solving the environmental problem, but dealing with the equity problem about people who are disadvantaged. So we were talking about this at dinner. I was discussing this question with 6th graders, and I asked them, what should we do about global warming? And they said, well, we have to get rid of coal, because they, after hearing discussion, realized it was the worst polluter. And then I said, well, how do you get the coal out of the ground? And one of them said, well, somebody said, well, you dig it out. Who digs it out? Miners. Do they have kids like you? Yeah. What happens to their jobs? I said. And one of them said, oops, we can't stop the coal. And another kid said, but then it'll be polluting if we don't stop it. I said, so what do you think we could do? And this was a 5th grader who said, well, maybe we could find something else that we could do to help the coal miners to work on. I wish this kid were a senator, because they haven't figured that out yet. And the problem is, not all solutions are binary. It isn't either they're employed or we pollute the environment. What we have to do is be creative and find ways that balance fairness and effectiveness. You can begin doing that at home. Ultimately, that can't make a major difference on the earth if you're the only one. But if nobody starts, then nothing happens. And then when you work up through toward international agreements, then working locally really makes a difference. And just because you won't stop at all doesn't mean we shouldn't try to stop, say, at least half. And we can certainly stop a quarter at negative cost. Half starts to cost real money. Beyond that is a fundamental lifestyle question. I can't tell you that'll be easy, but let's at least get slowing down, because that we can do easily. And then when we do it locally, we have some hope of having credibility of doing it globally. Thank you. Thank you. The geography quiz wasn't that terrible.